Hello, today we will continue solving problems on rotational motion with you and we'll consider the following question. A bicycle wheel with a radius in the post and a mass of 0.75 kilograms is subjected to a torque of 0.97 Newton meters. Considering the wheel as a hoop, find its angular acceleration and angular velocity after 5 seconds. How many revolutions will the wheel make during this time? So, we have a specific data set, and let's see that the radius of this wheel is given in centimeters. Let's immediately convert it into meters. Therefore, the international system we will connect. Well, now our task is to examine the actual process of solving this issue. Let's start by finding the angular acceleration, because we know the torque, and the wheel's parameters are also known, so we can recall Newton's second law for rotational motion, which allows us to determine the relationship between torque and acceleration. The only situation where you need to calculate the moment of inertia of the wheel, here we were told to consider it as a hoop, and I will remind you that the moment of inertia of a hoop is the mass multiplied by the square of the hoop as radius. Therefore, we are assembling the final formula with you. Mr. squared multiplied by alpha, break time 0.05. This is the formula for the moment, break time 0.04, and from here we can find the angular acceleration. So here we understand that if the torque does not change, then the angular acceleration will also remain constant, meaning this is uniformly accelerated motion. That is, regardless of when we calculate it, this value will remain constant. So we set the value and it turns out to be 0.97. Divide by the mass of the wheel, 0.75, and the radius squared, 0.35 squared. Thus we get an approximate value of 10.6 radians per second squared. So this will be the magnitude of the angular acceleration. Next, how to find the angular velocity if we know the acceleration and the rotation time of the given object. Here, essentially, we have a formula or law that determines the relationship between speed and time. Considering uniformly accelerated motion, the relationship turns out to be directly proportional. We also saw in the task that the process starts with an initial speed of 0, therefore we simply get the product of acceleration and time and can calculate. So 10.6 multiplied by 5 seconds. We get the speed in radians per second, and we get the answer, 53 radians per second. And one last question. We need to calculate the number of rotations the wheel made during this time. The number of revolutions might be a bit more challenging because it might not be immediately clear how to calculate this parameter, but let's recall another quantity with you, which is one of the fundamental ones describing rotational motion in general. This is angular displacement, which we will discuss together. We calculate from the perspective that the body rotates at a certain angle over a certain period of time. And then it can be said that the body made a certain number of rotations over a period of time, say in 5 seconds. Therefore, we can say that the total angle of rotation will be determined by the product of the number of rotations and angle of one revolution. The angle of one revolution is 2p. Thus, we can determine the total angular displacement of the given object and the number of revolutions it has completed during this time. And now our task is to recall how angular displacement is determined based on the set of data we have. We see that we know the angular acceleration, and we see that there is time. The acceleration of this object is known, and it is also known that the motion started from 0 velocity. Therefore, the most convenient formula for calculating angular displacement will be the formula that represents the dependence of angular displacement on time. Taking into account the initial speed of 0, we obtain the following expression. Now we can use these two expressions to find the number of revolutions. We get that n multiplied by 2p is equal to at squared over 2 or from here, if we find n, we get it squared divided by 4. After substituting the data, we get approximately 21 revolutions the wheel has completed during this time. Thus, we can connect the laws of rotational dynamics with the kinematic laws of this motion. Together, they provide a more comprehensive description of the process: acceleration, or conversely, deceleration of certain objects that may rotate. That's all for now. Our session is over. See you in our next lessons. Goodbye.